Hello and welcome to the Chem 1A pre-lab lecture for Experiment 10, Gasometric Analysis of a Peroxide Solution. Today's lab focuses on the ideal gas law, and we'll hope by doing this experiment that you will come to understand the law and learn how to apply it in calculations. The objective of your experiment today is to determine the amount of hydrogen peroxide in a percent weight by weight within an unknown solution, and you will determine this using the production of oxygen gas through the redox reaction of hydrogen peroxide with potassium permanganate. So once again, a reminder that in redox reactions, one element receives electrons and is thereby reduced, and another element loses electrons, and we call this oxidized. So in today's redox reaction, the manganese from our potassium permanganate is going to be reduced, and the hydrogen peroxide will be oxidized to water and oxygen gas. The ideal gas law is a convergence of Boyle's law, Charles' law, and Avogadro's law. Boyle's law can be summarized by, in a closed system, the pressure exerted by an ideal gas is inversely proportional to its volume. So if the pressure is to rise, then the volume will decrease. If the volume increases, the pressure will decrease. Charles' law looks at the relationship between volume and temperature of a gas and shows that the volume and the temperature are directly related. So as temperature goes up, volume goes up. As temperature goes down, volume goes down. Similarly, Avogadro's law considers volume and the amount of a gas and shows that those are directly related. And more importantly, Avogadro's law notes that all gases occupy the same amount of space at standard temperature and pressure. So this means whether we have a mole of oxygen or ozone or carbon dioxide, it doesn't matter which gas we're talking about, there will be the same number of atoms under the same conditions in a given volume. So if we render these expressions down to mathematical statements, we can say that the inverse relationship that Boyle saw between pressure and volume would be the expression of pressure times volume is equal to some sort of constant. In Charles' law, because volume and temperature are directly related, and if volume goes down, temperature goes down, we can say that the ratio of volume over temperature is also equal to a constant. Similarly, the direct relationship between volume and amount of gas can be summarized as volume over moles of gas is equal to a constant. So if we put these all together, PV was a constant, V over T is a constant, and V over N is a constant, while PV over N and T should also equal to a constant. And that constant is given the letter R and is called the ideal gas constant. The ideal gas law is usually expressed as PV equals nRT, or pressure times volume is equal to the amount of a gas times the ideal gas constant times temperature. It's important to note the units that are used with the ideal gas law. For pressure, we have a choice of whether we want to describe the pressure in terms of atmospheres or with the SI unit torr. Sometimes we also will see pressure in terms of millimeters mercury, and this has the same numerical value as torr. Volume is always measured in the SI unit liters, and the number of molecules is expressed in terms of moles. It's important to note that the value for the ideal gas constant will change depending on which pressure units you are using. If you are using atmospheres, the ideal gas law is 0.0821 liters atmospheres per mole per Kelvin. However, if you are using torrs in your pressure unit, the ideal gas constant is equal to 62.4 liters torrs per moles per Kelvin. Lastly, you'll note that the temperature is always measured in Kelvin. This is because we cannot have a negative value in our ideal gas law. For instance, if our temperature was -10, that would mean the expression on the right-hand side of the equation would end up with a negative value, since R is a constant and we can't have a negative amount of moles. That would mean that our PV expression would need to be negative. We cannot have a negative volume, and we cannot have a negative pressure. So in order for the entire expression to be valid, we need to use an absolute temperature scale. And the only absolute temperature scale that we have is Kelvin. At 0 degrees Kelvin, no pressure is exerted by a gas. This is because the molecules cease to move. So at 0 Kelvin, we would have 0 pressure, and so the equation is still valid. Let's look at some examples of where you may have seen PV equals nRT in your life. Remember how I mentioned that pressure and volume are inversely related. If something is inversely proportional, that means as one expression rises, the other decreases, and as that one decreases, the other one rises. And so you may have seen Boyle's law in action if you've ever gone for a car ride up into the High Sierra, up towards Shaver Lake, or even up to Sequoia National Park, and you brought a bag of chips with you. You may have noted that when you purchased your chips down here in Fresno, the bag was a little bit puffy, but you could easily squeeze it. But then when you got up to the top and you took out your chips to have a snack, the bag would be extremely taut and may have even popped open on its own. This is because as we rise in elevation, the atmospheric pressure decreases. And so our chip bag, which is filled with air to inflate the bag slightly, swells because the air inside the bag is increasing in volume. Pressure decreased, so volume increased, and your bag of chips becomes taut and close to bursting. You may have seen a direct relationship without having to even leave the valley. You may have noted that during our summer heat waves, your tire pressure gets very high inside your car tires. This is because temperature and pressure are on the opposite sides of our PV equals nRT, so pressure on the left, temperature on the right. So as temperature in the valley rises, the pressure of the air in your car tires will also rise. And so your tire pressure increases during the summer heat, and then if you go somewhere where it really gets cold in the winter, you may notice that the pressure decreases. So if you're someone who likes to keep your car tires properly inflated, you may need to let a little air out in the summer to not overinflate your tires. All right. So getting back to today's experiment, today we're going to do our experiment using a special apparatus that allows us to hold the pressure constant. And since we're not going to be heating or cooling anything, we can also assume that temperature is constant. So that any changes in our ideal gas equation is going to come from N and V. So we're going to look at the relationship between moles of gas and volume. Remember, this is a direct relationship. So as we have gas produced, so as the number of moles of gas increases, we should also see an increase in the volume. So specifically, when we react our hydrogen peroxide with our potassium permanganate, we are going to produce oxygen gas, and we will measure the production of the oxygen gas by a change in volume that we will measure using our modified burette system, pictured on the right. So just a little more detail on how the setup will work. In the Erlenmeyer flask, you will have a sample containing hydrogen peroxide and the catalyst sulfuric acid. You will then add potassium permanganate into a small vial and lower that vial into the Erlenmeyer flask. Without tipping any permanganate into your hydrogen peroxide solution, you will firmly cap the Erlenmeyer and raise your leveling bulb so that the level of water in the bulb and in your burette is equal. At this point, you have achieved atmospheric pressure in all parts of your setup. Next, you will vigorously shake your Erlenmeyer flask so that your small vial of potassium permanganate solution will spill into your hydrogen peroxide. Then a rapid chemical reaction will occur and oxygen gas will evolve. The oxygen gas will flow up out of the Erlenmeyer through the tubing into the top of your burette and push down on the water in your burette. While the water is being pushed down, it's important to have someone watching the leveling bulb and moving it down accordingly. This again will maintain atmospheric pressure in the system. This is going to be important in order to use the ideal gas law to calculate the moles of gas and also to help prevent any leaks in the system. The reaction that you are conducting today is really quite rapid, so it's good to spend a lot of time before you start the experiment making sure that your apparatus is gas tight and that you and your lab partner are communicating well with each other about coordinating, shaking the Erlenmeyer flask, and moving the leveling bulb. Also take time to make sure that you're getting the initial volume of water in your burette and you're measuring it to the right number of sig figs. Once you've seen the volume change in your burette, and again this will be quite quick, you'll just take a minute or two, determine the final water level in the burette and calculate the change in volume. This change in volume is the volume of your oxygen gas. Once you have the volume of your oxygen gas, you can begin to calculate the amount of oxygen produced and from that the percent hydrogen peroxide in your sample. There are 5 steps to this calculation, and I'll go through each of them one by one. First, we'll calculate the pressure of the oxygen gas from atmospheric pressure. At the beginning of class, your instructor will tell you what the atmospheric pressure is in the classroom that day. It's usually something around 760 torr, or 1 atmosphere. From your lab manual, you'll find a table that shows the water pressure at a variety of temperatures. Ask your instructor to also let you know the classroom temperature. Because water is always evaporating and condensing, there is some water vapor in the air above any vessel of water. So we need to subtract the pressure of the water from the atmospheric pressure to determine the pressure of our oxygen gas. So using the averaged pressure of the day being 760 torr and water pressure at an average room temperature of 22 degrees Celsius would be 19.8 torr. So subtracting 19.8 from 760, we're going to get approximately 740 torr. Now I'm doing this very approximately here because it's just practice calculations, but you will want to use all of the correct sig figs and maintain that throughout your calculation. Alright, so now that we have the pressure of oxygen equals to 740 torr, our room temperature was 22 degrees Celsius, which is approximately 295 degrees Kelvin. I know that I'm going to be using the ideal gas constant in terms of torr because that's what my pressure is. So that's going to be the 62.36 torr liter per mole per Kelvin. I can now enter in the volume change that I saw in my burette. So here my example is 8.52 milliliters. And remember that for the ideal gas law, we always need to be looking at volumes in liters. So I've just simply divided that by 1,000 to give 0.00852 liters. So now that I have these 4 values, I can solve for the remaining value, which is the moles of oxygen gas. So I rearrange the ideal gas law to solve for N. So N, so moles of oxygen gas, is equal to the pressure of oxygen gas times the volume change divided by the ideal gas constant times the temperature. And I've just plugged in my values here, done the calculation on my calculator, and I've found that the moles of oxygen gas produced is 3.43 times 10 to the negative 4 moles of oxygen gas. I now review my chemical equation to figure out the molar relationship between moles of gas and moles of the reactant that I was interested in, which was the hydrogen peroxide. We can see that there is a 5:5 molar ratio between hydrogen peroxide and oxygen. And 5:5 is the same as saying that there is a 1:1 relationship. This means every mole of oxygen gas produced came from a mole of hydrogen peroxide. Therefore, I would also have 3.43 times 10 to the negative 4 moles of hydrogen peroxide in my starting material. Now that I know the amount of hydrogen peroxide in terms of moles, I need to convert that to mass so that I can gain my percent weight by weight hydrogen peroxide, which was the objective of this experiment. So to convert between moles and grams, we need to use the molecular weight. I calculated the molecular weight of hydrogen peroxide to be 34.01 grams per mole. This is multiplied by the number of moles in my sample, the 3.43 times 10 to the negative 4, to give me 0.0117 grams of hydrogen peroxide. The last step is to simply divide the amount of hydrogen peroxide in my sample by the size of the sample itself. In this experiment, you used a volumetric pipette to deliver exactly 1.00 milliliters of sample into your Erlenmeyer flask. We can presume at low percentages of hydrogen peroxide that the density is the same as water, and so 1.00 milliliters of sample will weigh 1.00 grams. So I divide my amount of hydrogen peroxide, which was 0.0117 grams of hydrogen peroxide, by my 1.00 grams of sample, and multiply that by 100%. The result is 1.17% weight by weight hydrogen peroxide in my sample. You will repeat the experiment at least twice and take the average results to find the amount of peroxide in your unknown. In this experiment, we used the properties of ideal gases to analyze a sample for the content of hydrogen peroxide. We began by filling out as many variables of the PV equals nRT expression as we could, and then solved for the amount of gas produced. Once we knew the amount of gas, we related it to the stoichiometry of the chemical reaction with our reactant of interest, which was the hydrogen peroxide. We then used dimensional analysis to convert between the moles of hydrogen peroxide into grams and finally percent weight by weight. Whenever you're looking at gas law problems, begin by looking at what variables you already know and which variable are you trying to solve for. Then simply rearrange PV equals nRT to solve for that unknown variable. As I mentioned earlier, the most important part of having a successful experiment in today's lab is to take the time to make sure that your system is working and does not have any potential air leaks. Before you even collect any peroxide or acid or permanganate, simply test your system for leaks by plugging the Erlenmeyer and lowering the leveling bulb. If when the Erlenmeyer is plugged and you lower the leveling bulb, the water in the burette remains stationary, you know that you have an airtight system. Also, once you've collected your sample into your Erlenmeyer and have placed the permanganate vial inside the Erlenmeyer, cap it and test for leaks again before tipping the permanganate into your sample. Air leaks often occur at the joint between the rubber stopper and your Erlenmeyer flask, so it's very important if you've opened this to make sure that it's fully sealed again. Your lab instructor will let you know the day's atmospheric pressure and room temperature, but make sure you also record these for later reference in order to do your calculations. Please do not forget to factor in the pressure of water when you're calculating the pressure of oxygen gas. Because this is such a rapid reaction, it's very important that you do not let any permanganate encounter any of your peroxide before your system is sealed. So after you add the potassium permanganate to your vial, take some paper towel or Kim wipe and wipe out the outside of the vial to remove any of the purple solution from the surface of the vial. The sulfuric acid is a strong acid. It's a low molarity, so it's not especially dangerous, but please handle it carefully and wear gloves when handling the stock solution. Similarly, the potassium permanganate stains skin and clothing very badly, so make sure you're wearing gloves to protect your fingers and also button up your lab coat to prevent any unsightly potassium permanganate stains from getting on your clothing. This will be one of the first times that you're using a volumetric pipette in this class, and so your instructor will demonstrate how to use the bulb with the pipette. But remember that when you are adding your hydrogen peroxide to your Erlenmeyer flask, the pipette has already been calibrated to deliver exactly 1 milliliter with a little bit of liquid still remaining in the tip. As you can see in the picture here, there's a small amount of liquid remaining in the tip of this pipette. You do not want to blow out that liquid into your flask. That would add more than 1.00 mils. Okay, so let that last little drip hang there. Good luck on your experiment, and don't let the pressure get to you. Bye.